Hello everyone and welcome to my channel. My name is Pragati Jakati Mat and this video is part of my assignment of the course CML661. I will be walking you through the visualization of several important crystal structures using the Vesta software. The main goal of this assignment was to use Vesta, a powerful 3D visualization program, to model and understand the atomic arrangements in different crystalline materials. By looking at these models, we can better grasp concepts like coordination number, ionic radii, and how the structure influences the material's properties. Before we dive into the structures, let's quickly look at the one key concept that often relates to these materials, that is, ferroelectricity and the electric field. These slides introduces the hysteresis loop for ferroelectric materials. The vertical axis is polarization and the horizontal axis is applied electric field. Here is the key takeaway: when you apply a strong electric field, the material reaches its saturation polarization. When you remove the field, it doesn't go back to zero. It retains a you need to apply a field in the opposite direction called polarization force to bring this memory of polarization is what makes these materials useful for memory devices like found in some perovskites and other complex structures. This is the core of assignment. I have visualized 5 different crystal structures. For each one, I will tell you its name, its common structure type, and explain what is calcium telluride in the model or CaTe. This crystallizes in the rock salt structure, which is the same structure as everyday table salt NaCl. In this model, the green balls represents the Ca+2 cations and the purple balls represent the Te2 minus anions. The key feature of the rock salt structure is that each ion is octahedrally coordinated, meaning each calcium ion is surrounded by 6 telluride ions and vice versa. You can see this in a fractional coordinations. The cations and anions are arranged at equivalent positions, alternating in a 3D checkerboard pattern. The unit cell length here is 6.356 angstroms. Next we have gallium phosphide or GaP. This has the zinc blended structure which is common for many semiconductors like GaAs and ZNS. This is the structure. Both the gallium and phosphorus atoms are tetrahedrally coordinated. Each atom is at the center of a tetrahedron bonded to 4 atoms of the opposite kind. In my Vesta model, the violet balls are P3 minus anions and the green balls are Ga3 plus cations. The unit cell is 5.448 angstrom long. This tetrahedral coordination is crucial for the semiconducting properties of GaP. This is potassium oxide, K2O. It has what's known as the anti-fluoride structure. It's essentially the inverse of the fluoride structure, which we will see next. Here, the anions, the red O2 minus ions, form a base-centered cubic lattice, and the cations, the violet K plus ions, occupy all the tetrahedral sites. Notice there are twice as many potassium ions as oxygen ions, which matches the K2O formula. The coordination is different. Each O2 minus is surrounded by 8 K plus ions, while each K plus is surrounded by 4 O2 minus ions. The unit cell length is 6.449 angstroms. This is cerium oxide or ceria. It has the classic chloride structure named after the mineral calcium chloride, CaF2. This is the inverse of the previous structure. Here the cations, the red Ce4 plus ions, form a face-centered cubic lattice. The anions, the green O2 minus ions, occupy all the tetrahedral sites. So each calcium ion is coordinated with 8 oxygen ions, while each oxygen ion is in a tetrahedral environment coordinated with 4 calcium ions. This open structure is why materials like CeO2 are great oxygen ions conductors used in solid oxide fuel cells. The unit cell is 5.411 angstrom long. Finally, we have a gold zinc alloy AuZn. This has the simple cesium chloride structure. This is a very simple cubic structure you can think of. It has two interpenetrating simple cubic lattices. One lattice made up of yellow Au atoms has an atom at the body center. The other lattice made up of the black zinc atoms has atoms at the corners. So each atom is at the center of a cube with 8 atoms of the opposite kind at the corners. This gives a coordination number of 8 for both elements. It's a very compact structure and with a small unit cell of only 3.19 angstrom. It is a very dense intermetallic compound. We have successfully visualized and explained 5 different crystal structures: rock salt, zinc, blende, antifluoride, chloride and cesium chloride. Each has a unique atomic arrangement that directly determines the metal's physical and chemical properties. Using Vesta made it incredibly easy to visualize these complex 3D structures and understand the fractional coordinates.